711, you said? What number? Okay. .19 times 0.082. So we had to get our moles here. Do you know how to get the moles? Take this, move the decimal over so it's in liters and multiply it by this value, and that's how I got this. Then I did the same thing for this guy, and that's how I got the moles of the C2O4. And then you have to divide them by the new volume. So you got to add this volume and this volume together and get the new molarities. And then when you do that, you calculate the QSP by multiplying those two values together. And then that ended up being this value. Your K they gave you, where did we get K at? Oh, they gave you K right here. That's K. We calculated Q. K is less than Q, so it's going to form a precipitate. Yep. Because if you think about it, if you take that and think about that, you know, if you think about that in terms of like an arrow, right? If you set up K to Q here, and if you just add a line here, that means that the reaction is going to run this way. So that reaction over here is forming the solid. All right. Any other questions on that guy? Any questions on 711 or 712?
Number 2 on 712.
Number 2 on 712. All right. So we calculated the solubility here. We represented this with an X and an X. We know that KSP is this. So X squared would equal this. And then if you take the square root of that, that's going to give you your molarity of each of these. Down here, though, this is going to be, yeah, these are going to one. Oh, wait a minute. What did I do? Why did I not do the CA? Did I not change? Oh, I see what I did. Okay. Yeah, this is in, so we're figuring out the molar solubility for the CaCO3, but it's in this solution. So we already have some calcium in there. We're going to ignore the X because it's so significantly, it's going to be so tiny compared to what this 0.1 is. The 0.1 would overwhelm it. So then when you're calculating X, you're just going to simply do this. Now that value is less than this because we've already got some of that calcium in the water. So it's going to precipitate out a lot sooner in this solution than it would just in pure water. And that's the idea of the common ion effect. There's a common ion in there, and so because of that, it's going to cause it to precipitate out sooner. All right, what else is going on? Anything else in the homework before we move on? All right, so today we are covering the last two sections, which is 713 which deals with solubility, and then we're going to talk about 714. We just briefly gloss over 714, and we come back and pick that guy up when we get into Unit 9. So we need to know a little bit more information before we can really dig deep into that area. Did I give you 714? Maybe yeah, I did. Okay. All right. What did I do? Am I wrong? Is my scheduling wrong?
It says that it's 711 to 712.
Oh, okay. Well, this will give you an extra day to work on your progress check in your lab if you haven't got that in then.
Oh, yeah.
All right. So we're going to kind of briefly dip our toe into this section, and then we come back to this hot and heavy in Unit 8. Where we're talking about pH and solubility. So pH deals with acids and bases. And we talked about acids and bases. We talked about how our acid is, it donates a hydrogen, and how the base is going to receive it. So a hydrogen donor is your acid. And what I told you to do back in the day was to find the two different things that look similar and figure out which one has more hydrogen. The one that has more hydrogen is going to be your acid. Here, we look at these two. You can see that they're related. This one has more hydrogen, so this is the acid. The stuff on this side of the equation, we call them conjugates. So remember that vocabulary from first semester, hopefully, and last year in chem. All right. So we can get a K, this is called a Ka value when it's an acid condition. So we're dealing with a weak acid here. And water is not included. Why? It's a pure liquid. So we don't include that in our Ka value. Okay. So this is what that Ka expression would look like. You're going to have your products on top and your reactants on the bottom. This gives you a Ka value then. Addition of an acid would make the equilibrium shift left. So if we added an acid in, it's going to so if we added an acid in like HCl, so if we added like HCl in, okay, this hydrogen here is going to go and it's going to attach onto this base and it's going to form more of this stuff. And because of that, it's going to shift this direction to make up for it.
So adding more acid is more acid?
Right. So if we were to add like a strong acid or something other than this particular acid, okay? So if we added like a strong acid, right? So HCl would go and become H plus Cl minus, right? Okay. This H right here is going to attach to this guy right here. So we're actually pulling him out and we're actually creating more of this. So this is increasing. So if that increases, it's going to shift the equilibrium this direction. It's going to pull this guy out, make more of this, and then that's going to shift it over to this side. That's a lot of scrawling on there, y'all.
Okay. So if you add extra of one substance, it'll shift towards the other side?
Well, it depends on what the substance is, okay? So if the substance, like I said, if it's like an acid, like HCl, right? HCl is a strong acid. So you're going to get these hydronium ions or this hydrogen ion coming out. That hydrogen ion then is going to hook up with one of these waters. So essentially you're pulling this guy out and forming more of this stuff. So this is going to increase. If that increases, then it's going to shift this direction.
Yes.
Okay. Addition of a base then will make it shift the other direction because it's going to react with this to form more water. So this guy here will break out into H plus OH minus. The OH is going to hook up with this and it's going to make more water. I don't know that I explained that right. Hold on. Let me rephrase that. Yeah. So yeah, that I didn't explain that right. So what's going to happen is you're going to have the H3O plus. It's going to break up into an H plus H2O. That's better. This H right here then is going to hook up with that OH that's coming in and make more water. So if it makes more water, we're increasing the stuff on this side, and your equilibrium is going to shift this direction. Because you're pulling some of this out to make more of this, and then it's going to shift that direction to compensate. What is a base?
H3O.
No, H3O is an acid. Okay. We're adding in OH. So let's say that we dumped in a bunch of NaOH. Okay. Dump in a bunch of NaOH. That OH from the NaOH is going to cause this guy right here to split. The OH and the H are going to join together. You're removing some of this and forming more of this, so it's going to shove the equilibrium this direction then. Compensate.
So it doesn't happen to H2O.
Not the OH, no. So the H3O plus, right? What that is a hydrogen ion and a water, right? Okay. When you put in the NaOH, it's going to come apart as OH and then the Na, right?
Uh-huh.
These two things then will hook up and they're going to make H2O. Because you're increasing this amount, it's going to shift it, and you're pulling some of this out, right? You're pulling some of this out to make this guy. It's going to shift the equilibrium this way to make more of that. I just said you dumped it in. So you bought some and you dumped it in there. We also have a Kb expression when you have a base and then you've got water as your acid. This would be your Kb expression. And similar events happen with this that happened up here. So just kind of the reverse. All right. So here we've got our equilibrium. We have This guy over here is yellow. And this guy over here is going to be orange. Okay. So if we add in NaOH, that NaOH is going to hook up with what here?
The 2H. H2O. H2O.
It's going to hook up with this. Okay.
Yellow.
It's going to hook up with this. We're taking some of that away then, right? And we're forming this. So if we form more of that, this stuff over here is increasing. We're getting bigger and bigger and bigger. So then what's it going to do? It's going to shift what? It's going to shift over here and become yellow.
Does HCl connect to the H2O?
It's the H plus we're going to be working
Or
with.
the H plus connects
Okay,
to the H2O?
so the H plus here is going to come out. It's going to attach itself. H plus is going to shift. We're increasing this here. So if we increase this, right, then it's going to shift this direction and turn it orange.
But it connects to the H2O, right?
Does not hook up with anything?
Wait, where does it connect to?
Yeah, because you're increasing something that was already here.
Okay, so
So
whatever side is increased, then it shifts the other way.
Mhm.
Oh, I gotcha.
So if you only bases connect to stuff.
no, H's connect too. Yeah, what? Let me just think of here. H3O, H2O. No, we didn't have any. Yeah, we did have H plus. It's right here. Plus. The H made more of that. Okay, so down here. Okay, so down here, if it connects with this, yeah, if it connects with this, that makes sense. Yeah. If the H plus makes more of this, right? So it's going to make more of this. It's going to hook with a hydrogen. It's going to make more of this. And then it has to shift this direction to make more water.
Is this supposed to be for NaOH or is this for HCl?
If we're talking about this, you asked me if this attaches to something, right? So that H is going to attach to a water. That's going to form this guy, right?
Not HCl. Not HCl.
We're listening to the teacher.
Well, it is the H plus and H3O plus are the same things. These are synonymous. We just write this out when we're being lazy. Okay?
So the acid usually connects to the
Yep.
side, and then the base connects to the right side.
Well, it depends on what's set up where.
Or, yeah, so it depends where. Okay.
The HCl increases the products, and that means you have to shift back, right?
Yep, it's going to have to shift back. Yep.
And
Well, no, this H plus is going to increase this side here, which means it needs to shift this direction to make more. Brain done wrapping? Need to talk about it more? Okay. You might need to go home and process some of this and get it kind of in your own terms.
So
Okay?
when the concentration, oh, we're not up there, actually. I'm gonna guess. So I'm gonna say, no, but some of your thoughts. I'm gonna guess wrong. We'll convert.
All right. The next one. If we add in barium nitrate, okay, this has a very large KSP. So the barium, and then this has a small. So this guy right here is this guy right here, okay, and this guy is here. So this stuff here, when barium's introduced, it's going to stay in solution more than this would. This would come out of solution. So you would increase, if we had the barium, that barium would then come in, and it's going to create ions with, or it's going to create a solid with this. Okay, so this, some of this stuff is going to come out and it's going to settle as a solid down at the bottom. So we're removing some of this material out of here. Which direction is it going to shift?
Going to shift to the yellow side.
Yep, it's going to shift to the left and go yellow. All right, we are given these reactions here. They're asking us what will happen to the concentration of the Ca2 plus when the pH of the solution decreases.
It'll go down.
Okay, so if your pH is decreasing, it's becoming more acidic. Okay. So if we're getting more hydrogen ions in there, right? That's what acidic means. We have an increase in hydrogen ions. Yes? Okay. Then the hydrogen is going to come in and it's going to hook up with this guy and it's going to form H2CO3 minus, or actually H2CO3. Okay, hold on. H. Okay, so it's going to form some of this. All right, so the hydrogen is pulling some of this CO3 2 minus away. And it's becoming this weak acid here. So if we pull some of this away, what's going to happen to this? We're going to, yes, we're going to shift right. So we're going to make more of this, aren't we? Yes?
Yes.
So that's going to increase. They're asking what would happen to our Ca2 plus here. It's going to cause an increase in the Ca2 plus. Okay, everybody good with that? Making sense? All right, so you've got 2 problems there to work on tonight. And folks, we are going to our last section.
Yeah, there's so
Get over it. All right. So, when we look at reactions, there's something called spontaneity, okay? And it describes if a reaction will take place or not. So certain reactions will just take place without any external forces. I don't need to add electricity in. I don't need to do anything like that. They just happen, like the rust on my bumper, okay? The rust on my bumper is spontaneous. Now, it doesn't happen like that, of course. That took a long time to happen. So spontaneous in chemistry doesn't mean, boom, it's happening right this second. Okay? Spontaneous means that we don't need to intervene and add extra energy in to make it happen. Okay? So the rust on my bumper is a spontaneous reaction. Even though it takes a long time to happen, it just happens, right? There are 2 factors at play. The first of them is enthalpy. And enthalpy is the driving force. That is the heat. Okay? And we talked about that back in, I think it was Unit 6. The second driving force then is entropy. And that's often described as a disorder or randomness. It's kind of the number of microstates that can happen. So the probability of something getting together, okay, being distributed in these tiny little places around the container. Entropy is given with an S. And back, I gave you, I think it was in Unit 6, I gave you the tables, and one of them was like delta S. You had a delta H and a delta G. Do you remember that? The tables that had that in there for the different compounds? So your enthalpy is this guy, and your entropy is this guy. And the universe tends to move towards greater disorder. So I can clean my desk, and a week later, it's probably going to be back in this state again. Your closet, your room, depending on how much of a neat freak you are. Typically, the reactions, the measurements are given at 298 Kelvin. And that's typical room temperature, okay? As the temperature shifts, as temperature changes, then this will also change somewhat as well. So like I said, there are 2 other things that are linked together here. We have Gibbs free energy, which determines if a reaction is going to happen or not. If we have a negative Gibbs free energy, so if we end up with a negative value here, that means that it's going to be thermodynamically favorable for this to happen, for the reaction to happen. Delta H then is your heat, and this is your entropy value. The larger the negative value, the more the reaction will favor the products. If the enthalpy and entropy are both favorable, then the reaction will proceed. If enthalpy is unfavorable, then the reaction only proceeds at high temperatures. So for example, ice melting. Okay, if the temperature isn't high enough, the ice won't melt. entropy is unfavorable, then the reaction only proceeds at low temperatures, like ice freezing. And then if enthalpy and entropy are both unfavorable, then it doesn't proceed under any conditions unless you apply external forces. So this is what we're looking at, the intermolecular forces between, when we're looking at a solution forming, we have to look at the intermolecular forces between the solvent and the solvent are overcome. And that means that you're going to need some heat and you're going to need to increase your disorder. So when you take solvent particles and you break them apart, they work together. Now that you're breaking them into pieces, it becomes more disordered. So that's an increase in your entropy. Same thing with the solute particles. When they come apart, increase in entropy. When they come back together and reform, though, they're becoming more ordered, and that's going to give you a negative value. So, which solution here would have a greater entropy or disorder with all other factors remaining equal? A saturated solution of cobalt hydroxide or beryllium hydroxide? Which one of these is going to come apart more? A. Why? It has a higher K value, right? So this has a higher K value, so it's going to come apart. You're going to have more solute particles here. All right, the dissolution of calcium chloride here is exothermic. They want you to draw the following models, okay? So when we're looking at water, remember our water molecules. We have our water molecules, and they have the intermolecular forces here between the molecules, okay? And we're getting rid of those intermolecular forces with our water. Our calcium chloride was hooked together, something like this. Oops, shoot. In one of those matrix, and now they're going to come apart into individual ions. So you're going to end up with something like this. Okay. And then we're going to form an aqueous solution. So this is my positive ion. This is my calcium here. I'm going to end up with the water. I'm going to end up with the hydrogen surrounding on the outside of the water. It's going to come together like that. Okay. And then my negative ion here will have the water end surrounding it. Oh, wait a minute. Did I screw that up? Yeah, I did. Okay. Hold on. I can fix this. There. Sorry. Faster to fix it like that. This is negative, so no.
Yes.
Darn it. I said naughty word. I'm sorry, guys. Okay, let's try this again. I've got my positive calcium ion here. It's going to be attracted to the oxygen end of my water. There we go. Okay, my negative chlorine ion then is going to be attracted. This is my chlorine ion here. It's going to be attracted to the hydrogen end of the water. There we go. Better?
I guess.
And that is unit 7.
Horrible.
Oh.